Good morning, everyone. How are you all? Okay. So now we are going to start nuclear physics. In the previous lecture, we have discussed some questions of full syllabus test. Now in today's class, we will discuss about nuclear physics. Again, this is a very important topic. I hope we can cover it in one single lecture. Otherwise, I will take another lecture for the completion of this chapter. So let's wait and let's start. First of all, before this chapter, we have studied what is atom, what are atoms. By the discovery of Rutherford and by further continuation by Bohr, it is clear that atom contains a nucleus. So we will discuss about that nucleus. The topics are on your screen. The major portion, or you can say most important portion, is this one. The radioactivity. Lot of questions were asked recently from radioactivity. The radioactive decay law, half-life, nuclear fission, fusion. These are the most important topics. But today we will cover these topics. Try to cover these topics. Okay, moving further. First thing is, what is nucleus? I think everybody knows that nucleus is what? The central part of the atom which contains almost all the mass, For example, this is a central part of the atom. It contains protons and neutrons, whatever. Don't go with that protons are less, neutrons are more. Don't go with that. Don't see it like that. I have mentioned protons and neutrons. That's it. This is the nucleus which contains protons and neutrons. And one more thing I will add here. These protons and neutrons, or the particles which are inside the nucleus, are generally called as nucleons. Whether they are proton or they are neutrons, they will be called as nucleons. Another thing, remember the word. These particles, or you can say these nucleons, are bounded with strong nuclear force. Strong nuclear force. This is the strongest force of nature. Strong nuclear force is the strongest force of nature. The four fundamental forces, I think you know, and this is the strongest force. One more thing, what are the properties of this nuclear force? Or you will say this nuclear force is a short range force. Is a short range force. Another property of this nuclear force is it is attractive in nature. Attractive in nature. One more thing that I can add here, if the separation decreases, if separation is reduced, then at a certain position, at a certain position, it becomes repulsive. Mark my word, it becomes repulsive. So the main thing that anybody, if anyone asks that what is the nature of nuclear force, it is attractive. But if you decrease the separation between the two nucleons by a large amount, then at a certain distance, it becomes repulsive in nature as well. One more thing, that how we can represent this, it is generally represented by Z, X, A. Out of this, everybody knows that what is Z. Z are the number of protons, or you can say atomic number. I think this much of chemistry is known to everyone. A is what? It is generally called as mass number, or I will call it number of nucleons. I will call it number of nucleons. Nucleons means protons and neutrons. So that means total number of nucleons are A and total number of protons are Z. So how many number of neutrons will be there? Can anyone reply? Number of neutrons will be? How many number of neutrons will be? Total number are A, protons are Z, so that will be A minus Z. Is it clear? So now we know that what are the basic things of a nucleus? Bounded by strong nuclear force, short range force, protons and neutrons. It contains mass of proton and neutron is approximately same. Mass of proton and neutron is approximately same. Okay, moving further. Now, one thing that you will study by yourself is what are isotopes, what are isotones, what are isomers, and isobars. You just read it by yourself. Simple thing, you can read it. Moving further. Now there comes another relation. What is the radius of the nucleus? Radius of the nucleus is directly proportional to, or you can say radius of the nucleus is equals to, or directly proportional to mass number raised to the power 1 by 3. That is cubic root of mass number. And if you remove the proportionality, there is a constant R naught, and R naught has a value 1.2 into 10 to power minus 15, which is generally called as 1.2 Fermi. 1.2 Fermi. Femtometer, you know that. Femtometer is generally called as Fermi. Is it clear? One more thing, what is the density of the nucleus? If you see that density of the nucleus comes a constant number that is approximately 2.3 into 10 to power 17 kg per meter cube, which again means density, rho is representing density, is independent of mass number. Is independent of mass number. That means whether it's a helium, which is a lighter gas, you know that, whether it's a helium or whether it's a uranium, both will have same density. Both the nucleus will have same density. Oxygen, nitrogen, every nucleus will have same density. This is the important thing. Moving further. Now comes atomic mass unit. Atomic mass unit, the mass of protons, you know that it is very small, of the order of minus 27 kg. However, if I talk about of the order of 10 to power minus 27 kg, which is a very small amount of mass. So for measurement of those masses, we have created another unit of mass. Like for small masses, there is a unit gram, you know that. Kilogram is larger unit, gram is smaller unit. Similarly, there is a very smaller unit, which is atomic mass unit. The definition itself says 1/12 of the mass of one carbon atom. Which carbon atom? 6 carbon atom. It has many isotopes as well. So which carbon atom they are talking? 6 carbon 12 atom is defined as 1 AMU. That means mass of 6 carbon 12 atom, 1/12 of this mass is defined as 1 AMU. This is the definition here that I have mentioned. Now, if you calculate these values, it comes out to be 1.6710 to the power minus 27 kg. Now, based on that, mass of proton is approximately 1 AMU. Mass of neutron is also approximately 1 AMU. 1 AMU, if I am talking, that is 1.00 something. You need to remember. But it is easier now to calculate the masses. Moving further. Now there comes the most important relation of the chapter. Einstein's mass energy equivalence. First thing, I have mentioned two formulas. Look at the first formula. Einstein's mass energy relation. What Einstein said, you need to understand the statement of Einstein. What he said. According to him, according to him, if suppose there is a mass m, generally from mechanics we know that it may have some kinetic energy, it may have some potential energy. Two things are there. And with thermody, we somewhat know that it may have some internal energy. So three kinds of energy we have studied till now. But Einstein says any mass can be converted into energy. Mass is just a concentrated form of energy, and any mass can be converted into some form of energy. And this energy that it possesses is called as rest mass energy. Is called as rest mass energy. So what I am saying, according to Einstein, every mass has some energy due to its mass only, not due to motion, not due to position, not due to temperature. It has some energy due to its mass. And this energy is called as rest mass energy. This energy is known as rest mass energy. Now, the name you should remember. Now, this energy is calculated by Einstein as such that E is equals to m into c square, where c is what? Speed of light. Is the first statement clear? Every mass can be converted into energy, and this energy is due to its mass only, not due to position, not due to kinetic energy, not due to motion, not due to thermal energy or temperature. It's due to its mass and known as rest mass energy. Now, the second statement. Before Einstein, everyone says that mass of the universe is conserved and energy of the universe is conserved. These were two separate things. These were two separate things. Now, Einstein came and he says that no, mass is alone not conserved, energy alone is not conserved. What is conserved? The sum of these two is conserved. The sum of these two is conserved. So, according to Einstein, the another statement, which is very famous statement, says the sum of mass and energy of the universe is conserved. This is the second statement of Einstein. I have chosen universe here. You can say the mass and energy of an isolated system is conserved. The sum of mass and energy of an isolated system is conserved. This is the another statement. What does it mean? If in a system energy increases, then mass must decrease. If mass increases, then energy must decrease. This is the relation. And what is the value of this energy? Is given by delta E is equals to delta M into C square. That means if mass changes by delta M, then energy will change by delta E. This is the again most important relation. These were the two relations given by Einstein. Moving further. Okay. Now, according to Einstein, mass is equivalent to energy. That's what we have seen. Mass is equivalent to energy. How much energy is M into C square? So, how much energy is equivalent to 1 AMU mass? That means if you have 1 AMU is atomic mass unit, 1 AMU mass, it is generally represented by somewhere 1, and AMU is generally represented by U. This is again 1 atomic mass unit. You can call these two interchangeably. Now, 1 AMU mass is equivalent to 931.5 mega electron volt. 931.5 mega electron volt. And if you don't know, electron volt is a unit of energy, and 1 electron volt is equals to how much? Can you comment? 1 electron volt is equals to 1.6 into 10 raised to the power minus 90 joule. Everyone should remember this as well. Clear? Okay. Moving further. What is the meaning of this? For example, if I know that energy equivalent to 1 AMU is this one. Now the situation comes, I have told you if mass decreases, then energy will increase. So if I say that in a system, mass is changed by 2 AMU, mass is changed by 2 AMU, then what will be the energy? What will be the change in energy? So you will clearly say that you know the formula delta E is equals to m into c square. But I will say don't use that relation, because in this case you need to put c and then square it, then multiply it. Don't use it. Delta E is equals to mass is 2 AMU and 1 AMU is equivalent to 931.5 mega electron volt. This is going to be easier. So whenever you know the mass in terms of AMU and you want to calculate energy, then just multiply by 931.5 mega electron volt and you will get your answer. Is the last statement clear? You are not going to use this one. You will use this one. If you want energy and mass is known, then use this one. Moving further. Clear now? Okay. Now there comes another term, very important term, binding energy. Listen to my words very carefully now. You can read the definition. Binding energy means the energy required to separate the nucleons of a nucleus. Or in another terms, you can say the energy by which the nucleons are holded together in a nucleus. Now listen to me. This is a nucleus. This is a nucleus. And I want to separate these blue and you can say orange or red, whatever. These circles represents protons and neutrons. And I want to separate these nucleons. So for that, they are bounded together by some force. So we need to separate them. And for that, we need to give some energy. So let's suppose I have given some energy. I have given some energy. And by this energy, I have separated the nucleons like this. Every nucleon is at a large distance as compared to each other. Or you can say the nuclear range, the nuclear force, the range of nuclear force is very small. So we have separated them by a large distance according to that. Now, one more thing. Listen to me. From this position to this position. Now you can say the nucleus was like that. And I have given some energy to it and I have opened it like this. Clear? Like this. So during this process, I have given some energy. During this process, I have given some energy. So according to Einstein, due to this energy, the mass of the system will increase. So mass of the system will increase. That means if this one has a mass m1 and this one has a mass m2, then m2 will be larger than m1. Why? Because this m2 contains mass of the nucleons plus some energy. So what I say, in this process, m2 will be greater than m1. m2 is what? Mass of all the nucleons. Mass of all the nucleons. And m1 is what? Mass of the nucleus. However, nucleus contains those protons and neutrons only. But when these protons and neutrons are separated, the total mass increases due to this energy which I have given or someone have given. I can't give them energy. So m2 is greater than m1. That means there is some mass defect. There is a difference in mass. And this difference in mass into c square, can you say that this is going to be the energy? So this energy is called as binding energy. Again, I am repeating, the energy required to separate the nucleons. So this much energy I have given to separate the nucleons. And due to this energy, some mass defect is created. And this mass defect is, let's suppose, delta M. Why I am saying it mass defect? Because by separating, there is some additional mass. So this delta M into C square. This mass defect is created by this energy. So this energy will be equivalent to delta M into C square. And this is known as binding energy. This is known as binding energy, where delta M is what? Mass defect. Delta M is called as mass defect. Again, I have mentioned this relation, but you don't need to use this term delta M into C square. You can write it, but whenever it is required, you have calculated delta M, then multiply by 931.5 mega electron volt, and you will get your energy. Moving further, mass defect. So, what is mass defect? I think it is clear till now that mass of separated nucleons is more than the mass of nucleus. So, what is the difference of these two? So, for example, if I say that nucleus is ZXA, this is the nucleus. So, for this nucleus, I am going to write the mass defect. This is the nucleus, and these are the separated nucleons. Clear? It contains protons and neutrons. So, mass defect, if I write, okay, first of all, tell me which mass will be more? The mass on the right side of your screen, this one, or mass on the left side of your screen? Which one will be greater? YouTube community, don't be quiet. You can also comment. It will not take a lot of time. Okay. So delta M is what? Mass of nucleus minus mass of nucleon. Mass of nucleons minus mass of nucleus. Okay. Very good. Right side. Right side. Okay. Very good. Chichuni and Veena, you both are there. Delta M is equals to mass of nucleus minus mass of nucleus. I'm saying wrong. Mass of nucleons minus mass of nucleus. So number of nucleons, if I say, let's suppose mass of proton is MP, mass of neutron is Mn, and mass of nucleus is M capital N. Now, I am writing mass of proton is MP. How many protons are there? You can say Z protons are there. So ZMP plus mass of neutron is Mn. How many neutrons are there? You will say A minus Z neutrons are there. Clear? This is the mass of nucleons minus mass of nucleus, and this is going to be delta M. This is going to be mass. Okay. Okay, not able to enter. Okay, no problem. I hope that there must be some problem with that. Zoom link is not opening. Okay. Okay, is this point clear? Delta M, how we calculate delta M? Now you know how to calculate mass defect, how to calculate binding energy. Now there are few punchlines. Mark those punchlines very carefully. and write it. Definitely, you should write. You must write, in fact. What I am saying, this is the punchline. What it says, that if there is a tightly bound nucleus, if there is a tightly bound nucleus and you have given it some energy, then it may convert into loosely bound nucleus. Or in fact, the other term that I will most preferably use, or I will use preferably, is that if a tightly bound nucleus converts into a loosely bound nucleus, then in this process, some energy is required. In this process, some energy is required. Or another term, if a loosely bound nucleus, the process is reversible. You can see that the arrow is going both the ways. If loosely bound nucleus converts to tightly bound nucleus, some energy is released. Some energy is released. So this is most important term. Read it with me. If loosely bound nucleus converts to tightly bound nucleus, then some energy is going to be released in the process. Clear? This is the basic phenomena of nuclear fission and fusion. That's why energy is released in the fission and fusion. Loosely bound nucleus converts to tightly bound nucleus and some energy is released. This is the phenomena. The reverse arrow that I have shown is the phenomena of nuclear fission and fusion. The nuclear bomb, hydrogen bomb, everything works on this principle. So remember this line. Next, binding energy per nucleon. This is again another simple term, binding energy per nucleon. What it says, it is denoted by binding energy is E, B. Per nucleon is A. EBA is called binding energy per nucleon. It is nothing but binding energy divided by number of nucleons. Binding energy divided by number of nucleons. This is called binding energy per nucleon. The most important thing or most important key line or punch line in this, more binding energy per nucleons. If I say more binding energy per nucleon means more stable nucleus. That means the more the binding energy per nucleon, more will be the stability of the nucleus. Now understand one or two things more. Binding energy per nucleon means average energy required to eject one nucleon. That means a nucleus contains a lot of nucleons. Out of those nucleons, the average energy required to remove one nucleon is called as binding energy per nucleon. That means if binding energy per nucleon is more, that means to remove one nucleon, you need more energy. You need more energy. For example, this is a nucleus and it has some protons and neutrons like this. And binding energy per nucleon is 8 mega electron volt. This is for atom A. For nucleus A, there is another nucleus B, for which nucleon is 6 mega electron volt. What does it mean? It means that to remove one nucleon from this atom, we need 8 mega electron volt. And to remove one nucleon from this, we need only 6 mega electron volt. That means these are tightly bound. These are tightly bound and these are loosely bound. Can you understand this thing? Can you understand this thing, that how we can identify that which is tightly bound, which is loosely bound? The nucleus which has more binding energy per nucleon, mark my word, per nucleon, will be tightly bound, and which has low binding energy per nucleon is known as loosely bound. That means it is less attracted by the nucleons together. So if now tell me, give me the answer. If A converts to B, if A converts to B, energy will be required or it will be released? Anyone tell me. If A converts to B, energy will be required or it will be released? Veena, Chichuni, Dilip. Be quick to respond. If A converts to B, that means tightly bound to loosely bound. The atom is going. For this process, energy will be required. Very good, Veena. And if B converts to A, then energy will be released in the process. Clear? Very good. Okay, moving further. Now, binding energy curve. I am drawing a binding energy curve, a rough binding energy curve. So don't compare it with the one that you have in your books. I am drawing a rough idea, giving you a rough idea of binding energy curve. Very good, Sushant. So binding energy curve, basically a curve between number of nucleons. Number of nucleons means that you will say mass number, A, and the binding energy per nucleon. This energy is in mega electron volt. So what is seen? This curve is something like this. This is the rough diagram. So not to scale or not to everything. But major thing is, this is the maximum binding energy, if I say, and this is for iron. And this energy or binding energy per nucleon is approximately 8.5 mega electron volt. Approximately, I will say. So one thing, one question that you can remember, the highest binding energy per nucleon is for iron, which is approximately, I am writing it again, approximately, which is something 8.5 mega electron volt. You can correct me if there is some other number. It is approximately 8.5 mega electron volt. Now thing is, what is the main thing? Two or three things. Initially, if the mass number increases, then binding energy somewhat increases. And after that, it starts decreasing. So this is, if I say uranium 238, this binding energy is approximately 7.3 or 7.4 mega electron volt. This is for uranium. Now, one or two things more. This range, you can see, is uniform. The binding energy per nucleon in this range is approximately uniform, not changing much. So this range is called as stable range. The nuclei in this range are stable. In this region, there are two more regions. This is a stable region. And these two regions are unstable because binding energy per nucleon is less. Per nucleon is less. So one more thing, these are the heavy nuclei. One heavy nuclei in this region may break into two or more nuclei of this region. This is region 1, this is region 2, this is region 3. 3 is stable, 1 and 2 are unstable. So nuclei in this region 2 may break into region 3, and in this process is known as fission. This process is known as fission. And in the fission, you can see that if these are loosely bound because they have less energy, these are tightly bound. So in the fission process, loosely bound nucleus converts to tightly bound nucleus and some energy is released and large amount of energy is released. This process is known as fission. In the same way, in this region, what happens? Fusion. Two light nuclei combines to form a heavy nuclei and the process is known as fusion. In both the processes, energy is released. So binding energy curve, I have explained. What are the main things? As mass number increases, binding energy first increases, then decreases. Highest is for iron. Highest is for iron, approximately 8.5 megaelectron volts. And what is fission? In which region fission happens? In which region fusion happens? And why energy is released? Everything is clear. Moving further. Moving further means there are some questions for you. Now you will do the questions. Two nuclei have their mass numbers in the ratio 1:3. Very good. The ratio of their nuclear densities will be. I need that answer from you. I need that answer from you. I am waiting for 30 seconds only. And within 30 seconds, every one of you must answer. Dilip, Sushant, Veena, Tichuni, Isaac, Isaac. It's a name that I have heard, Isaac Newton. Or Isaac is what? Newton was, the full name of Newton was Isaac Newton, no? I hope so, if I am not wrong. Answer it, answer it. Two nuclei have their mass numbers in the ratio 1:3. The ratio of their nuclear densities will be. I told you nuclear density is a constant. Nuclear density is what? It is constant. If it is constant, then nuclear density will remain same. Whatever be the ratio of their mass numbers, the nuclear density will remain same. That is 1:1. Clear? Moving further for the next question. If the nucleus, one is aluminium, has a nuclear radius about 3.6 Fermi, then what would be the radius of this? What is this? I don't know. Selenium, what is this? You know. So they are talking about the ratio of radius or the radius they are asking. So if I say, everybody knows radius is directly proportional to a raised to the power 1/3. Is it clear? Now, ratio of radius R2 by R1 will be A2 by A1 raised to the power 1/3. Clear? Again, what does it mean? R2 by R1 is equals to A2 by A1. If I say 125 and A1 is what? 27. That is 125 by 27 raised to the power 1/3. And if you calculate, it will become 5/3. So R2 will be 5/3 R1. And R1 is mentioned as how much? 3.6 Fermi. That will be 1.2. That will be 6 Fermi. Which is correct option? 6 Fermi. Correct option is D. Clear? Moving further. How does the binding energy per nucleon vary with the increase in number of nucleons? Again, this is the same question that I have asked. I told you. Decreases continuously with mass number? No. First decreases and then increases? No. First increases and then decreases? True. Increases continuously? Wrong. So which is correct option? C. Okay. Moving on to the next question. A nucleus with mass number 240 breaks into two fragments, each of mass number 120. Okay. Listen. Let's suppose this is 240. It breaks into two nucleus, each of 120. That means it breaks into 120 plus 120. The binding energy per nucleon is given. For unfragmented is 7.6 and that for fragments is 8.6, 8.5 mega electron volt. The total gain in the binding energy in the process. Total gain in the binding energy or the energy released in the process, both the things are same. They will ask you the same question, different questions, but answer will be the same. So how these two things, this Q is the energy released, or you can say Q is the change in binding energy. So that change in binding energy, or I will say Q, is equals to binding energy of product minus binding energy of reactant. I think everybody knows what is the meaning of reactant and what is the meaning of product. These two are the product and this is the reactant. Now, one more thing. Binding energy of product is Y, but this is, mark my word, this is binding energy, total binding energy, not per nucleon. So binding energy of Y will be, we know that binding energy per nucleon is 8.5. That is 8.5. And how many nucleons are there? 120. Are you able to understand? This is the total binding energy. You know the relation of binding energy per nucleon is what? Binding energy upon number of nucleons. And binding energy of reactant means X is what? 7.6 is the per nucleon multiplied by how many nucleons are there? 240. Now we need to place this value only. Binding energy of product, there are two Y components or two Y elements. That means 2 times of 8.5 into 120 minus 7.6 into 240. Can you see that out of this 240 is common? 120 into 2, that means 240 is common. What will be remaining? 8.5 minus 7.6. What will be the remaining? That is 2 into 120 into 0.9, I think. Is it clear? So you can cancel this decimal with the 0. And that will be 12 into 18. 36. 216 mega electron volt. 216 mega electron volt. So mark my words, you have not focused that what I have told you, the change in binding energy or the gain in binding energy is nothing but the energy released in the process. So Q is the energy released. This energy released, you must remember this formula, which is binding energy of product minus binding energy of reactant. So the energy released in the process is this one. If somewhat this energy comes to be negative, if this energy comes out to be negative, for example, if it comes out to be minus 216 mega electron volt, then it means that energy is not released, but the energy is absorbed in the process, and it is known as endoergic process. And if Q comes out to be positive, it is known as exoergic process. You know the term exothermic and endothermic, I hope. So if energy released, it is known as exoergic. If energy is absorbed, it is known as endoergic. Clear? Moving further. Okay. One more question is there. The binding energy per nucleon of, you can understand this is C lithium 7 and 2He4. Nuclei are 5.6 and 7.06 mega electron volt. In the nuclear reaction, this one. The value of Q released is energy released, they are asking. That means the same question is there. Binding energy is given, but mark my word, binding energy per nucleon is given. So what you will write here, I will not solve this time, that's for sure. The formula for Q value is binding energy of product minus binding energy of reactant. There are two reactants and two products. Clear? So what you should do, while this is binding energy per nucleon, 3Li7 is 5.6 mega electron volt. So complete binding energy will be 5.6 into 7. So binding energy of lithium will be 5.6 into 7. Can you solve it? And similarly, you can get it for helium as well. And then put in this relation, you will get Q. You will get Q. Clear? So I'm not. You will. This is just a calculation based thing. Now comes radioactivity. Before moving to alpha decay, beta decay, or gamma decay, I will tell you one thing. When a nucleus becomes unstable, a spontaneous emission comes out of it to gain the stability. What I am saying, when a nucleus is unstable, whenever a nucleus is unstable, a spontaneous emission, this is a very long spelling, I will say, spontaneous, you can understand that emission takes place, and this spontaneous emission is called as radioactivity. What is the meaning of spontaneous emission? The meaning of this is nothing is required to initiate this emission. A nucleus is unstable, it automatically emits some particles known as alpha, beta, and gamma particles, and these particles are spontaneously emitted. That means no other chemical, physical reaction activity cannot alter this thing. That means if radioactive emission is taking place, you cannot stop it by changing the chemical composition, by changing anything in the atmosphere. You cannot stop it. It is going to happen. That's why the Hiroshima and the other name, that is Nagasaki. You cannot stop the emissions. You cannot stop the radioactivity by any means. So this is a spontaneous process. So one thing, the energy involved in these processes is of the order of mega electron volt. Mark my words. The energy involved in these processes is of the order of mega electron volt. The chemical reactions that you study in your chemistry classes, those chemical reactions are of the order of few electron volts. So this energy is very less. The chemical reaction does not have that much energy so that they can alter the radioactivity decay, radioactive process. They cannot alter. One thing. Now, when alpha decay comes out, when the nucleus becomes very heavy, when the nucleus becomes very heavy, some particles emitted from it, and alpha particle is one of them. And this alpha particle is nothing but helium nucleus. Helium nucleus. What happens? Let's suppose this is ZXA, a nuclei ZXA, and this is called as parent nuclei. Out of this, a helium nucleus is ejected. Helium nucleus is nothing but alpha particle is ejected automatically, spontaneously. What remains is another nuclei which is called as daughter nuclei. This is known as daughter nuclei. In the complete process, some energy is also released, which is known as Q value, which is known as Q value of the equation. And one more thing you can see here, the atomic number is decreased by 2 and the mass number is decreased by 4. Or another term that you can say, that Z thing and A thing will remain conserved in the process. You can see that here mass number is A, and if you add these two mass number is again A. That is 4 plus A minus 4. That is again A. That means mass number in a process remains conserved. Similarly, proton number also remains conserved. That you can see that Z will remain same. What is the value of Q, or what is the amount of energy released, is mass of reactant minus mass of product into C square. Mass of reactant minus mass of product into C square. Very good. Now there comes beta decay. Beta decay is of two types. One is negative beta decay, one is positive beta decay. Negative beta decay happens when there are more number of neutrons in a nucleus. When neutrons are more as compared to protons. When neutrons are more, then one neutron converts into a proton inside the nucleus. One neutron converts into a proton and one electron is released. And in the process, some unknown particle, anti-neutrino, is also released, which is somewhat massless particle and chargeless particle. And some energy is also released. What's happening? Neutron converts into a proton and one electron is released in the process. This is known as beta decay. So in beta decay, you can say that neutron decreases by 1 and proton increases by 1. For example, this is a parent nuclei ZXA. Beta decay happens, one beta particle, this is negative beta particle or known as electrons, is ejected. In the complete process, you can say number of nucleons will not change. Why? Because one neutron is decreased and at the same time one proton is increased. That means number of nucleons remains same. So A will remain same. Protons are increased by 1, so that is Z plus 1. Anti-neutrino plus energy Q. One more thing you can notice here. Again, the mass number and proton number are conserved from LHS and RHS. This is daughter. Q value can be calculated by the same way, mass of reactant minus mass of product into C square. Moving further. Beta positive decay. When the nucleus contains more number of protons, then proton converts into a neutron and one positron. This is known as positron. And some energy is also released. And this is known as neutrino. This is known as neutrino. Positron, neutrino. And now how the reaction will look like? Can you see that? Proton is converted into a neutron. That means proton is decreasing, number of proton decreased, and number of proton increased. So number of mass number will remain same, because mass number is what? Number of nucleons, they are same, but proton is decreased by 1. And again, you can see that the Z number and A number are conserved. One more thing. This Q value is the energy released in the process. And this energy is carried out by beta particle, neutrino, and this daughter nucleus. This energy is carried out by beta particle, neutrino, and daughter nucleus. All of these carry this energy. This energy is not like that, boom, energy is released. No, this energy is carried out by the particles. By the particles. Clear? One or two questions you can solve. After that, we will end the class. Question says, a radioactive nucleus ZXA undergoes spontaneous decay in the sequence something like this, where Z is the atomic number, the possible decay particles in the sequence are. So first of all, they are saying there is ZXA. It converts to Z minus 1, B, then converts to Z minus 3, C, then again converts to Z minus 2, D. So the question is, which of the following is the sequence? Which decay is first taken place? First, in first step, which decay according to you is happening? Z number is decreased by 1. That means protons are decreasing. And proton are decreasing. That means which decay is this one? Positive beta decay. If Z is decreasing by 1, that means proton is converted into neutron and proton converts into neutron in positive beta decay. Clear? Now in the second case, Z is decreased by 2. That means alpha particle is ejected, because alpha particle has two helium, helium nucleus. So this is going to be alpha particle. Now again in this, say this is Z minus 3, this is Z minus 2. That means there is an addition of one proton. There is an addition of one proton, and one proton is addition means neutron is converted into proton, and which is negative beta decay. So how you can remember this? Negative beta decay means negative beta decay, N for negative, N for neutron. That means neutron converts to proton. That means neutron converts to proton. You can remember like that. Clear? So what is the correct sequence? Positive beta, alpha, negative beta. Positive beta, alpha, negative beta, which is option number D. Clear? Sorry. After 1 alpha and 2 beta emissions, this is not the real question. Which beta they are saying? Negative beta. ZXA. 1 alpha, if you remove, it will become Z minus 2 Y A minus 4. Clear? And if you remove another beta particle, negative beta particle means neutron converts to proton. That means proton number is increased by 1. That is Z minus 1. Let's suppose this is some another nucleus B. A minus 4 will remain same. Again beta negative particle. So it is again increased Z. It is become C and A will remain same, A minus 4. Is it clear? So which option is correct? One thing is atomic number will remain same in the process. So they are saying atomic number increases by 2. That means this is wrong. Another thing you can see that parent nuclei has at mass number A and this has mass number A minus 4. That means mass number reduces by 4, which is option number B, which is correct. And all other are wrong. So which is correct option? Option number B is correct. So in this class, we will study till to this point. In the next class, we will discuss about radioactivity, which is again a most important topic. Most of the questions are going to be asked from radioactivity, the half-life, the mean life, the emissions. Those were the questions that are going to be asked. The decay constant, whatever, activity. So we will discuss that in the next class. Till then, bye everyone.